Hello, hello. Welcome back. This is my second time recording this because the first time my microphone was muted for some reason. I don't know why, but here we go again. So let's look at example 6. Same matrix as before. This time, instead of asking to find a few vectors in column A, like find a vector in column A like we did, where we just had to do any linear combination that you wanted. This time it's giving us a vector and we want to know if it is in column A, in the span of these three vectors. In other words, does this vector equation have a solution? If it does have a solution, there exists a way to write the vector 12, 21 as a linear combination. And so it is in the span of the columns. So we do the usual thing where we rewrite this as a augmented matrix of the corresponding system of linear equations. And then we can row reduce it using the same sequence of row operations we did in the last example. Actually, instead of doing that, let's notice something. When we row reduced A before, we found that A was row equivalent to the following thing here. Like A itself, this is A, was row reduced to this. And doing these steps would result in some kind of unknown stuff here on the right, but we don't need to know about that because we know that A has pivot positions in every row. And so the existence theorem says that this equation here is consistent no matter what you have on the other side. That, in other words, the column space of A is equal to all of R2. And this vector is definitely in R2. So yes, it is in the column space. All right, what about this one? Is this in the row space of A? In other words, does this vector equation have a solution? Is there a vector in the row space that is equal to 5, 7, 10? So this time we've really got to solve it. We know that this is the augmented matrix for the corresponding system of linear equations. And we can row reduce this. The goal is to get zeros below this 1 in the top left. That will be a pivot position. And now we know this and this will be a pivot position. We can clear out that -6 by doing -2 row 2 plus row 3 to replace row 3. And that gives you an augmented matrix where there is a pivot in the rightmost column, which of course means that equation in that row says 0x1 plus 0x2 equals 1, which is always false. So this definitely has no solution. So is this vector in the row space of A? No. So yeah, finding if a vector that's given is in the row space or the column space involves solving a system of equations. But if you want to know if a vector that's given is in the null space of A, we just need to use the entries here as weights of the columns of A and see if the result is 0. And just doing the scalar multiplication and vector addition gives you the following. And if you combine all the root 7 like terms here, then yes, you will get 0 and 0 for each component. So this vector is a solution of the homogeneous equation. Cool beans. Let's look at theorem 1.3. Subspaces are spans. We already know that every span of some vectors is a subspace. But do we know that if you have a subspace, then it is a span, that all subspaces are spans? This theorem says yes. It says that if W is a subspace of Rn, then W is equal to the span of some list of vectors, some linearly independent list of vectors, v1 through vc in Rn, and the number of those vectors is less than or equal to n, the number of entries in each vector. Okay, now we're going to do a proof of this in a minute. The proof is a little technical. I think it's cool, but it's more important to kind of get an idea for why this is by maybe looking at some examples. So let's look at the different kinds of subspaces that we have so far as examples real quick, and notice that they are spans. So yeah, we already proved that all spans are subspaces. In 1.4, we showed why null spaces are spans. Here is where we went over the reasoning for why the null space of anything can be written as a span, and we did several examples of writing the null space of a bunch of matrices as spans. Okay, so yeah, null spaces are spans. We have this example here in exercise 2, the warm-up. This set was a span, and it satisfied the definition of a subspace. So this subspace was a span, sure. Here is a subset that is not a subspace of R2 because 2 of the conditions were false. And it's also not a span. If it was a span, you would be able to get linear combinations of the vectors and stay within it. So yeah, the fact that this is like limited, that it has this edge here, means you can get out of it using scalar multiplication. So example 4, maybe that's an extra credit question to say, like, what are the vectors that you can write to get this as the span of those vectors? All right, so yeah, maybe you have kind of an idea why it's true, a little bit of intuition from these examples. Here's a proof. I think the proof is cool. If you're going to skip some of the videos, some bits of these videos because you don't have time or you need to take a nap, now's a good time to do that. That's okay. The stuff after this will be more important, but this is a cool proof. I like it. I'm going to show it to you. I hope you think it's cool too. So we're starting with the if part. If W is a subspace of Rn, that means we're really assuming that W is a subset of Rn that satisfies all 3 of the conditions, but I'm not going to write all that out. What we want to do is find the list of vectors, describe somehow, show that a list of vectors exists that makes this work. And this is going to be a proof sort of by induction. By the way, I got this proof from Sheldon Axler's book, Linear Algebra Done Right, but I think the proof is probably much older than that book. But it's a good book. Anyways, we're going to do this multi-step process. Step 0 is going to be, first of all, if W is the smallest possible subspace of Rn. Let's get this out of the way. Then W is equal to the span of the empty list. That's why we had those weird edge case definitions for that before. And we said the empty list is defined to be linearly independent, and the definition of the span of the empty list is just the 0 vector. Okay, so in that case, we're done. So we can skip the rest of the proof. Otherwise, there must be some non-zero vector in W. And let's just call that non-zero vector v1. So now that we have that, let's look at step 1, the next step. The list just containing v1 contains a single non-zero vector, and we had a theorem in the last section that said that was linearly independent. So it might be the case that W is just equal to the span of v1. In that case, we're done. We found a list that is linearly independent and spans W. We know the span of v1 is a subset of W. Everything in the span is also in W, since W is closed under scalar multiplication, because we assumed it's a subspace. So now it might be that everything in W is also in the span of V1. And in that case, we're done, because we have this linearly independent list of one vector that spans W. And we can skip the rest of the proof because we've proved it. But if that's not the case, then there's something in W that's not in the span of V1. Next, we're going to go on to step 2. Now, we know that because V2 is not in the span of V1, V2 is not a multiple of V1. And we know V1 is not equal to 0, and that means theorem 1.6, which says that if a list is linearly dependent, then one of the vectors can be written as a linear combination of the preceding vectors, as long as v1 is not 0. So that means this list is linearly independent. And we also know that, again, since W is closed under scalar multiplication and vector addition, that the span of these, any linear combination of these two vectors, is still in W. At this point, it might be the case that W is equal to the span of V1, V2. Then we have a linearly independent list that spans W, and we're done. Otherwise, there's a V3 vector in W that's not in the span of V1 and V2. And at this point, the rest of the steps are going to be basically the same. So we're going to write out what is step I. So we repeat this process some number of times, and we're going to show that this process must eventually end. So this list of I vectors now is linearly independent because V3 is not in the span of V1 and V2. Vi was chosen, so it's not in the span of the previous vectors. And every time you do this, you're getting a vector that is not in the span of the previous vectors. So, and the first one is still not equal to 0, so it's linearly independent by theorem 1.6. And we can still say that the span of all of them is a subset of W, since it's closed under scalar multiplication and vector addition. Now, it might be that W, we finally have enough, that W is equal to the span of all of them. Otherwise, we can get another vector Vi plus 1 that's in W, but not in the span of the previous ones. And then we continue the process as long as it takes. But at some point, the I is going to be bigger than n, bigger than the number of entries that are in each vector. Because at that point, you're going to have a linearly dependent list. Because a list of more vectors than entries in each is linearly dependent by whatever theorem that was in the last section. But we know at every point the list is linearly independent. So we can't get to a point where we have more than n linearly independent vectors. So that means when this ends, you must have a point where the vectors span W. So yeah, basically, you can keep choosing vectors that are linearly independent from the previous ones in the list, but you can't do that forever. And the only way this can stop is when you get to this step here. So that point must happen at some point. So I think that's a neat theorem. I think it's a neat proof. And what this also says is that the following corollary is true. A corollary is just like a theorem that follows directly from a previous theorem. This says a subset W of Rn is a subspace if and only if it can be written as the span of a list of vectors. So, yeah, subspaces are spans and spans are subspaces, but they're two different ways of looking at the same thing. One is as the set of all linear combinations, and one is as a set that satisfies these three requirements. Cool beans.